AC voltage controller. So here the one AC, this is an AC, we are converting into another AC. This AC RMS is less than the input AC. So AC voltage controller, so here the RMS values of the output we are controlling. So this is an inputs and this is passed through two SCRs T1 and T2 connected in anti-parallel, and here we are considering the load. Here we have shown resistance as a load. So that's the reason we are considering resistive loads. A feature of resistive load is the current is in phase with voltage. Okay, so this is a single phase bidirectional controller with resistive load. This is an input. So in the positive half cycle, first when the input is in the positive half cycle, the thyristor T1 junction J1 and J3 is forward bias, correct? So anode is made more positive than cathode. So if we apply the gate pulse at some firing angle, here the firing angle we have chosen here is 60 degree. We are applying a gate pulses to this transistor T1, he has shown like G1. We need to consider that G1 is a current pulse or a voltage pulse which we are applying to the thyristor T1. We have applied somewhere here, that's the reason T1 turned on. SCR T1 is turned on. T1 is acting like a wire, means it is short circuit, means it is acting like a wire. So the input is connected to the source. Right now T1 is passing the current. T1 is acting like a conductor, it is acting like a closed switch. So ideally we assume that there is no drop across the T1, but there may be a small drop nearer to 1 volts, but we can neglect for smaller waveforms drawings and simple calculations. So right now what I am saying here, when input is in positive half cycle, we are applying a gate pulses to this thyristor T1, so T1 turns on. So so then once this turns on, it is acting like a wire. So the load is connected to source, load is connected to source. So the current is flowing from current is flowing from source to load, okay, source to load. So source to load, okay. So current is flowing from source to load in this way. So current, this is my current direction, Then in the next firing angle, we are firing T2 in the next negative, in next half cycle, in the next half cycle, like in negative half cycle, we are firing T2, we are firing T2, we are firing T2 somewhere here, okay. This is at if you fire the thyristor T1 at alpha, we need to fire thyristor T2 at pi plus alpha. So then T2 conducts, T2 conducts, T2 conducts. You can see here in the negative half cycle, this side is more negative, and this side is more positive. So this thyristor T2 is forward biased, So if we apply a gate pulse, somewhere here, okay, so then the current is moving in this direction, So current, this is my current direction in the negative half cycle. As soon as you apply a gate pulses to this gate and cathode, if we should apply a gate pulses in between gate and cathode, okay. So in the positive half cycle, as soon as we apply the gate pulses here, so the thyristor T1 is turned on, so then, so my SCR T1 conducts, is conducting, so if you consider that there is a supply here, it is coming from the transformer secondary, here you will have a transformer, okay. So you can see this current is flowing in this direction, okay. So whatever current is flowing here is this shown here, okay. You can see this is on, so it is acting like a short circuit. There here it is, so to this you can see here, this is acting like a short circuit, So load is directly connected to source. So what is a load voltage? If somebody asks you what is a load voltage, load voltage is same as my input voltage. That's the reason load is receiving the voltage in this way, So at pi you can see here my input goes to negative, so my thyristor T1 turns off, because in the negative half cycle this side is more negative compared to this side, so negative is connected to your anode of SCR, so this thyristor turns off, and no current flows to the load here onwards. There is a reason zero voltages. Somewhere here we are applying gate pulses to the thyristor T2, That's a reason thyristor T2 turns on at pi plus alpha. So once it is turned on, it is acting like a short circuit. It is acting like a closed circuit. So in the negative half cycle, in the negative half cycle, negative half cycle, so this side is positive and this side is negative, so the current is moving like this, in this way, and in this way. So at that moment this is conducting, so this is conducting. So that's the reasons. Now also the source is connected to load, but through this SCR, so once SCR turns on, it is acting like a closed switch. So what about load voltage? Load voltage we are getting same as my input, but in my input is in negative half cycle. That's the reason I'm getting this voltage. So this is my waveforms. This is my waveform. Okay. So we have seen the load voltage. So here are shown the load current. Why load current is lesser than the voltage means current formula is V by R. If V is having some value, it is divided by R. R is if it's 10 ohm, so it is divided by 10 ohm. So current is 10. If it is R is 10 ohm, the current is 10 times less than the voltage in all the instantaneous values. Same current in the negative half cycle also flows. So we have seen now how circuit works. Okay, I can show you the simulation of the circuits. Okay, so next I can show you. See here, this is one SCR which is conducting this is an SCR which is conducting in positive half cycle. This is an SCR which is conducting in a negative half cycle. This is a gate pulse which is used to fire an SCR at positive half cycle. This is a gate pulse which is used to fire an SCR, another SCR which works in negative half cycle. You can see here, here we have chosen a firing angle of 45 degree. That's the reasons for a first SCR delay time I have chosen as 2.5 millisecond. So we need to understand that 20 millisecond is 360 degree. So 2.5 millisecond means 445 degree. So but here delay time is 12.5 millisecond because pi plus alpha. 10 millisecond means pi, 2.5 means 45 degrees, so 12.5 milliseconds. So if I run this circuit, you can see here the load voltage changes. So this is my input voltage. Whatever I am showing here is input voltage. So you can see here input voltage. We can, okay, for timing we'll remove that. Okay, so whatever we have shown here is a load voltage. Where we need to measure load voltage, we need to measure across a load. So here we have measured it. So whatever you have seen is a load voltage. You can see the load starts at 45. Load voltage starts at 45, ends at pi. Again it starts at pi plus alpha, ends at 2 pi. If you consider the current waveforms here, you can see here current waveforms. I can show you current. Only this is a current waveforms. The current is going till 15 amps and it is coming back to minus 15 amps. So whatever voltage is, so I will remove this current right now. I can show you the voltage. Voltage is going to 325 volts and minus 325 volts, but current is very less. Okay. If I show in a same scale, you can see here manual limits. can see here current this 360 and okay. Next, so if I put in the same scale 480 amps, 80 amps, see the current is very small because current amplitude is very small. So if I increase the resistance value, you can see I will put some 5 amps, reduce it. So So this is my voltage waveforms, this is my current waveforms. One feature here we need to understand, the current is in phase with the voltage. Okay, so we'll go back to my PPT. Okay, so we have seen that this is my input and this upper one is my voltage waveforms. So this is my voltage waveforms. This is my voltage waveforms. This is my voltage waveforms. So if you look at this, this completely looks like this. So this is 0. This is ideally we said it is 0, but it is maybe some 1 volt is there because that is a drop. But for all calculations here onwards, I will consider it this part. Whenever it is off, it is 0. This is 0. Same waveform repeats here onwards. Okay. So if you consider this input is also AC, input is also AC, the output is also AC. It consists of positive parts as well as a negative part. So current is flowing in one direction in positive half cycle, and in the negative half cycle it flows in the reverse direction. So it is AC only. So one form of AC we have converted into another form. Difference here, the RMS value of this output voltage is less than this. So if there is some incandescent some bulb, if you are applying this voltage to this bulb, it is giving you less light compared to the lights which is emitted when you have given this supply. If it is a 230 volt RMS, if the RMS values of this is 230, definitely this is its RMS value is less than 230. Okay. How to calculate the RMS voltage for this waveform? That is our next job. What we need to do means we need to take root mean square value of this waveforms. So you can see whatever I have shown in the red color. So this waveform's root mean square value we need to take. This waveforms looks like sinusoidal from alpha to pi, and it is sinusoidal from pi plus alpha to 2 pi. Pi plus alpha to 2 pi. We will take a root mean square value of this waveform. This waveforms. So here you can see here VRMS of the load, is it visible? VRMS of the load, if it is not visible, so it is, so this is 2 pi, so 2 root, so this is nothing but root, this is, I will write here, root of, so 1 by 2 pi alpha to pi Vm sin omega t whole square d omega t plus pi plus alpha to pi Vm sin omega t whole square d omega t. Because you see in here in the previous screen, from alpha to pi, so from alpha to pi it is started, from 0 to alpha it is 0, so we need to start integrating from alpha to pi, that's the reason we have started integrating from alpha, and we went till pi. Then what is the nature of this Vm sin omega t? So we have taken whole square of that, because we need to take root means square. Then again the next part of this waveform starts at pi plus alpha. This angle is pi plus alpha, and it will go till 2 pi. So it reaches till 2 pi. Okay, so there is a mistake here, we need to write it as 2 pi. Okay, pi plus alpha to 2 pi Vm sin squared omega t d omega t whole square. So then you can see that alpha pi sin omega to d omega t, this Vm you can keep outside, Vm square 2 pi d omega t, pi plus alpha 2 pi sin omega t whole square d omega t. Then simple trigonometry rules we are using, Vm squared, then 2 pi alpha to pi integration, sin omega t, sin squared omega t we can write as 1 minus cos 2 omega t divided by 2, sin squared omega t we can write as 1 minus cos 2 omega t divided by 2 d omega t. Sin pi plus alpha to 2 pi, similar formula we are using here. Then so 1 integration omega t limits alpha to pi, cos 2 omega t integration sin 2 omega t divided by 2 limits alpha to pi, plus again here omega t limits pi plus alpha to 2 pi, minus cos 2 omega t sin 2 omega t by 2 to pi plus alpha to 2 pi. Then Vm squared by 4 pi, this is pi minus alpha, because of pi minus alpha, sin 2 instead of omega t pi, sin 2 pi by 2 minus sin 2 alpha by 2 plus 2 pi minus alpha minus sin 4 pi 2 by 2 minus sin 4 pi plus 2 alpha, 4 pi 2 alpha by 2. So Vm squared by 4 pi, pi minus alpha, so sin 2 pi is 0 minus sin 2 alpha by 2, pi minus alpha. So here you can see sin 4 pi is 0, so then it is sin 4 pi 2 alpha divided by 2, so this is sin 4 pi plus 2 alpha is sin 2 alpha by 2, okay, pi minus alpha minus sin, so minus and minus is there here, okay, Vm squared by pi minus alpha, this minus comes out plus sin 2, my pi minus alpha plus sin 2, 4 pi, so 2 pi cancel, 2 pi minus alpha minus 2 alpha, sin 2 alpha by 2, sin 2 alpha by 2, sin 2 alpha. So Vm squared Vm I have taken outside, so it becomes Vm. This 2 I have taken outside, it becomes root 2. This 2 pi I have kept same there. 2 pi minus 2 alpha sin 2 alpha. This 2 I have divided 1 by pi I have kept inside, I kept out, and this 2 I have taken in pi minus alpha sin 2 alpha by 2. So it looks like Vm by 2 root 2 means always this RMS voltage of source. If any waveforms, if you know the Vm, if it is purely sinusoidal waveforms, it's what is the RMS of that? Vm by root 2. Vm by root 2 is my source voltage RMS. This is nothing but V source RMS, means RMS of the source voltage. This is nothing but RMS source voltage RMS. V source RMS into this is same thing. This is my final formula. V RMS of load. So what is the thing? V RMS of the load it is. Whatever this is, V RMS of the load. V RMS of the load. You can write in any format. You can write load here also. VRMS of the loads, we got the formula. Okay. Next. So we have studied circuit, waveforms, and its RMS of the loads. So what is the final conclusion? By changing alpha, we can change the RMS of the loads by changing alpha. Source voltage RMS, how much we need to deliver out of source voltage, that we can deliver by changing alpha. Means by changing firing angle of T1 and T2. Alpha means that is a mean. Next. So theory, I think we understood. So this is very used, where this AC voltage controller is extensively used. Maybe in if it is an R load or if it is an RL load circuit operation will change a little bit, but this bidirectional AC voltage controller is extensively used. Then you take one problem. So a single phase full wave AC voltage controller has a resistive load of R is 10 ohm and input voltage is 120 volts, 60 hertz. The delay angle of a thyristor T1 are equal alpha 1 pi by 2. Alpha is pi by 2. Determine the RMS output voltage. Then input power factor, the average current of the thyristors, the RMS current of the thyristors. All these things we need to learn now. Okay. So now we'll take this problem. So you write the circuits, circuit diagram is the same circuit. This is my circuits. Okay, circuit. So he's saying that so alpha is 90 degree. So I can show you how my waveforms looks like. And this becomes 5 millisecond, correct? Then this becomes 5 milliseconds, 15 milliseconds. Okay. So this is my waveforms. So this is my waveforms. So this is my voltage waveforms and this is my current waveforms. So this is my voltage waveforms and this is my current waveforms. Okay, so for this we need to find out what is average what is the RMS voltage of the load. What is an RMS voltage of the loads? Okay, so we'll go back to problems. So we have understood what is a problem. So I think this is your circuits we need to refer. Okay, first of all we need to calculate what is an average voltage. Okay, what is the first questions he is asking? He is asking us to calculate the RMS output voltage. What is the formula for V0? So we need to write what is the formula for RMS values of the output voltage. You can call this as V output RMS or V load RMS, anything is okay. LOAD, load RMS you write. Some people will write this as V output RMS, both are okay. I will use this term V load RMS. Okay, what is the formula we have derived already? What is the formula we have derived for RMS load? This is a formula V source RMS, V source RMS into root of 1 by pi minus alpha plus sine 2 alpha by 2. This is alpha. So it is easily we can calculate what is the source RMS. See, one thing I will tell you, we can use it as a source RMS or else some formula it looks like Vm by root 2 into same thing, both formulas are okay, correct? 1 by pi minus alpha plus sine 2 alpha divided by 2. See, we need to understand what is the difference here. Here it is written as V source RMS. Here it is written as Vm by root 2. Both are same. Okay, Vm by root 2 is also source RMS. Here in a given parameter we can calculate Vm and we can divide by root 2, or else using given parameter we can directly use the source voltage RMS. Okay. So V load RMS is equal to, what is a V source RMS? He has given input voltage RMS is 120. So if you are directly writing, if I am using this formula, I am using here 120. Okay, then 120. I am using the term V source RMS. Otherwise, for 120, what is a VM? That we need to calculate. What is a VM? VM becomes something like 325.2 something you will get. 325 point something you will get. Okay. Then divided by root 2. You can check this is also equal to 1. He's saying that 120 RMS. We need to calculate what is the value of VM. 120 into root 2. That is a VM. VM. Okay, 120 into root 2. So divided by root 2. So what is you will get? 120 only you will get. You will get 120. That's the reasons we can directly use 120 here. Then, so 1 by pi, what is the firing angle pi? What is the firing angle? Pi by 2, plus sine 2 alpha, 2 into pi by 2, divided by 2. Sine pi minus pi by 2 is pi by 2. Okay, so if I will write it neatly, 120 into root 1 by pi, pi minus pi by 2 is pi by 2, plus sine 2 into pi by 2. These two cancel each other. These two cancel with this. So it becomes sine pi. Sine pi is how much? 0. So sine pi is 0. So this equal to 120 is there outside. 120. So this equal to 120 1 by pi into pi by 2. So pi cancel each other. So finally what happens? 120 by root 2. This is your answer. So can you tell me what is an answer? What is the value you got for this problem? So 84.85. 84.85. So 84.85 we got. What is that? Volt, capital letter V. So this is output RMS voltage or load RMS voltage. So RMS values of the load or load RMS, anything you can write, load RMS or RMS of load or output RMS or RMS of output, anything you can say. Okay. So he called it as what is he has asked the RMS of the output voltage. You can call as better as per his, you can call as instead of calling as a load, you can call as V0 RMS, means output voltage RMS values. Okay. You can use this term or this term, or you can use he has used in a textbook, he has used capital letters, so you can use capital letter better, capital letter. Okay. Next, what is the next part of the question? Is the input power factor. The input power factor. The power factor means the output power divided by source voltage into source current, or else I can say that source power. We call this as VA. If it is in mega volts, some MVA, because in high power we call as MVA because it is mega volts amps. So here it is volt amp. This is talking about the source voltage RMS, and this is talking about source current RMS value. This is the load power, or else the power which we have delivered to load, or else I can say that output power. So power factor is output power divided by V into A. What is output power? Here the source output voltage is also, or a load voltage is also AC, correct? So V0 output voltage RMS into output current or load current RMS divided by VA. V means source voltage, okay, source voltage RMS, A means amps, means current, input current RMS, input means source current RMS. So this is equal to, what is the formula for VO RMS? VO RMS formula we have studied so just before. So we are having a VO RMS formula, correct? No, this is source RMS into this. Okay, so we'll write that. Okay, so or else we have already calculated VO RMS. How much? 84.85. We can write 84.85 into IORMS. What is that? This is a question. Okay. So one more thing, this I need to talk a little bit about. Then V source RMS is known to us or not? Yes. The source RMS is how much? 120 watt. Okay. So this is 120 volt. 120 volt. Okay. Now I need to think about IORMS and ISRMS. The load current RMS value and source current RMS value. I will go back to my circuit. See here